Good afternoon, everybody. I have selected a topic on rings. As you know already, groups. Group is the meaning of star is a binary operation and it satisfies the four axioms like closure law, associative law, identity law, and inverse law. Based on this, what is the meaning of ring? A ring is a set R together with a pair of binary operations addition and multiplication satisfying the following axioms. The first axiom is R is an abelian group under the operation addition. Second axiom, the operation dot is associative, that is A dot of B dot C is A dot B of dot C. The third axiom, the operations satisfies the distributive laws. That is, for all A, B, C belongs to R, we have A plus B dot C is equal to A dot C plus A dot B dot C. That is called right distributive law, in shortly called as RDL. And A dot of B plus C equals to A dot B plus A dot C. That is called left distributive law, shortly called as LDL. And the type of the rings are, say one is a zero ring. The additive identity is called the zero of the ring and is written as O. That is 0 dot A equals to A dot 0 equals to 0 for all A is an element in a ring. Commutative ring. A ring R plus dot. Here plus addition dot multiplication. These are the binary operations. Is called the commutative ring. If the dot is commutative, that is A dot B is equal to B dot A for all A comma B belongs to a ring R. Another definition, unity of the ring. A ring R plus dot is a ring with unity if there exists an element denoted by 1 such that A dot 1 is 1 dot A, it is A. For all A is a member of R. Hence, 1 is the unit element or the unity of the ring. For one point is, under multiplication always 1 is the identity element, whereas under addition 0 is the identity element. Another definition, say division of a ring. A division is a ring in which the division is possible. Specifically, it is a ring in which every non-zero element A has a multiplicative inverse. That is, there exists an element x with A dot x is x dot A is equal to 1. Now I am selecting some examples on a ring. The first example is prove that the set of all even integers is a ring. Now we'll start with its solution. Consider the set A is equal to 0 plus or minus 2 plus or minus 4 plus or minus 6 and so on, because the given set is even. In this case, first we have to show that the first condition of a ring is addition is a abelian group or abelian group is under addition. So first of all we show that it is an abelian group, means closure, associative, identity, inverse and commutative law holds. Just I will discuss one by one. For all xy belongs to 2 set. So why I am selecting 2 set? Because the given set is even. Therefore x plus y is belongs to 2 set. Thus closure law holds good or satisfied. Then come to associative law. For all x, y, z belongs to 2 set, then x plus of y plus z is x plus y of plus z. Then identity law. In the given set, 0 is one of the identity element. Therefore, 0 belongs to 2 set such that x plus 0 is 0 plus x is equal to x for all x belongs to 2 set. And fourth law is a inverse law. The fifth law is commutative law. X plus y is equal to y plus x for all xy belongs to 2 set. Thus all 5 axioms are holds, hence it is an abelian group under addition. Then second axiom is the associative law under multiplication. Again for all xyz belongs to 2z, therefore x plus x into of y into z is x into y of z. Then third axiom is a distributive law, that is x plus y of z is equal to x into z plus y into z for all x, y, z belongs to 2z. Another illustration of a ring is, consider the second order matrix is also one of the ring under addition and multiplication. The question is, prove that the matrix ABCD for all ABCD belongs to R is a one of the ring with respect to addition and multiplication of matrices. Again, is a ring means we have to satisfy all the 3 axioms just one by one. The first axiom is show that it is an abelian group under addition. Consider the two different matrices related to the given matrix, that is M1 and M2. So M1 matrix is A1 B1 C1 D1, that of M2 matrix is A2 B2 C2 D2. Then start with first law is a closure. M1 plus M2. Addition of two matrices is a one of the matrix. Thus it is belongs to M. Then associative law. M1. In case of associative law, consider one more matrix, say M3. M3 matrix is A3 B3 C3 D3. Therefore, M1 plus of M2 plus M3, which is M1 plus M2 of plus M3. Therefore, associative law is also true. Then, in identity matrix, always 0 matrix is the identity matrix. Therefore, given matrix, addition to 0 matrix, we get the given matrix, that is A, B, C, D. And inverse law, given matrix A, B, C, D plus minus A minus B minus C minus D, we get the result is a 0 matrix, because our definition of inverse in group is A star A inverse is always equal to an identity matrix. Here the given matrix is identity matrix. Then come to the third part of that. Another illustration from the ring is, prove that the set R of numbers of form A plus B root 2 for all ABC, AB belongs to R is a ring with respect to ordinary addition and multiplication. That point is very important. Again, consider first integer, say z1, a1 plus b1 root 2. For of z2, a2 plus b2 root 2. Here all a1, b1, a2, b2 are belongs to the set of integers. Under addition is z1 plus z2. We get a1 plus b1 root 2 plus a2 plus b2 root 2. That equals a1 plus a2 plus b1 plus b2 into root 2, because root 2 is common. This itself the given form a plus b root 2. Similarly, in case of associative property, consider another integer, say z3, because already z1 and z2 selected in the first law. The third integer is say z3, and that is a3 plus b3 root 2. Again it's a sum, we get always LHS must be equal to RHS. Therefore, associative law holds. Again, in case of identity law, 0 is the identity element. And inverse law, that is a plus b root 2, its inverse is minus a plus of minus b of root 2. When we have to add these two, we get 0. That is our definition holds. And lastly, commutative law is for all z1 and z2 are the given integers. Therefore, z1 plus z2, which is z2 plus z1. Thus, it is an abelian group under addition. Then associative law. Associative law under multiplication. That is our second axiom. z1 into z2 into z3, always z1 into z2 of z3. Therefore, associative law satisfied. Then distributive law. z1 into of z2 plus z3 always equal to z1 into z2 plus z1 into z3. So already z1, z2, z3 given integers are mentioned. You simplify and verify the result. And z1 into z2 of z3 equals to z1 into z2 plus z1 into z3. So for both LDL and RDL holds, hence the given set of integer is a ring. Then what is a finite ring? A ring containing finite number of elements is called a finite ring. A ring contains an infinite number of elements is called an infinite ring. But the definition of infinite ring is not mentioned here. Just you write the definition and complete it. For one more important illustration for examination point, in a ring R, if xy whole square equal to x square y square, for all xy belongs to R, then show that R is a commutative ring. That means xab is equal to ba. This is our general definition of commutative property. Just we are using that definition here to show R is a commutative. The given thing is xy whole square equal to x square y square for all xy belongs to R. Just I am simplifying the given hypothesis is xy whole square is nothing but xy into xy. For left side, right side, x square is xx, y square is yy. Again, by using associative law, can be written as x times yx into y is x times xy into y. Certainly, by applying a cancellation law for both left as well as right, we get directly xy is equal to yx. That indicates the given ring is a commutative ring. Similarly, in examination, instead of xy, you can write AB whole square is equal to a square b square for all ab belongs to R, or any other notations are given, you rectify and solve it. The definition for another one is a Boolean ring. A ring R plus a dot. Here one point is, remember, R plus a dot indicates it is an algebraic structure. Basically, what is algebraic structure? A structure containing more than one binary operation, that is nothing but algebraic structure. That is already discussed in a group. Similarly, a ring R plus a dot is a Boolean ring if a square equal to a for all a is a member of R. For example, if a square equal to a for all a belongs to R, then R is again commutative. But one thing, in this example only one member is given. We have to select one more element related to the given thing. That's our first plan. How? Let AB be one of the elements in a ring. So already a square equal to a means similarity case b square equals to b. Here for both a and b are the members of a ring. By using these conditions to show R is a commutative. Since AB belongs to R, so that A into B also belongs to R. Again, AB whole square equals to A square B square. Just it is based on the above example, clearly AB equals to BA for all A and B are in a ring. This means R is said to be commutative. Then one more important definition for examination point, zero divisor. If A and B are two elements in a ring with A is not equal to 0, B is not equal to 0, but product of the two elements equals to 0, then A and B are called zero divisors. In case of non-zero divisors, the difference is A is not 0, B is not 0 also. Product is also not 0. That type of the divisor is called non-zero divisor. A not 0, B not 0, product becomes 0, is a zero divisor. A is not 0, B is not 0 also. Its product is also not 0, that is called non-zero divisor. That's a point. Then we are discuss some of the properties of rings. So just like 2 marks question asked, at least one of the property in your question paper. So for one property is, if R is a ring and ABC belongs to R, then A into 0 is 0 into A, it is 0. But in this property, only one element is enough. A belongs to R. But for the next property, all elements are considerable. Here, the clear question for first property is, if R is a ring and A belongs to R, that is enough. Then A into 0 is 0 into A is a 0. Then how to start with this proof? So A into 0 equals to 0. Actually, it is our given thing. But here, A 0 plus 0 is 0. We know that always 0 is the additive identity. 0 plus 0 equals to 0. Just I am writing operating on left both sides by an element A. What will get? A into 0 plus 0 equals to A into 0. By using distributive property, left side can be written as A into 0 plus A into 0 equals to right hand side A into 0 plus 0. It doesn't change. Again it implies A into 0 plus A into 0 equals to A into 0 plus 0. That implies A into 0 equals to 0 because by left cancellation law. Similarly, on right distributive law is also proved same thing. 0 plus 0 equals to 0. Here, element should be written on the right side of the LHS. That is 0 plus 0 into A is equal to 0 into A plus 0 into A. Again, we are using distributive property as well as right cancellation law. We get the result. This is the first property of a ring. Then second property, if R is a ring and A comma B belongs to R, then A of minus B is equal to minus A of B equals to minus of AB. So the proof of this property is again A of minus B plus B equals to A into 0, where minus B is the additive inverse of plus B. Implies that A into minus B plus AB equals to 0, because as already we know A into 0 equal to 0 by above property. That is A into minus B plus AB equals to 0 by left distributive law implies A of minus B equals to minus B AB, because plus AB shift into the RHS. Similarly, for the other case, for right distributive law, again A of minus B equals to minus A of B, each must be equal to minus of AB. Then in the third case, third property, if show that R is a ring for all A, B, C belongs to R, then A of B minus C equals to A of B plus of minus C. That must be AB plus of A of minus C is equal to AB minus AC. These are some of the properties related to a ring. With the help of the definition of ring, what is a subring? Its meaning is, let R be a ring, a non-empty subset S of the ring R is said to be the subring of R if and only if is a ring under the two induced operations. With the help of this definition, one of the theorem is, take an element A, of course A is non-zero, a unit in a ring R with unity, then A cannot be a zero divisor. The proof of this is, suppose not. Suppose A is a left zero divisor, there exists B is not equal to 0, and also B belongs to R such that A times B becomes a 0. Suppose A is a unit element, so for that inverse of that element is exist. Consider A into B equals to 0. So operating A inverse on left on both sides, we'll get A inverse of A into B is A inverse into 0. Consider the associative property, we get A inverse into A of B equals to 0. But by definition of inverse, A inverse into A becomes 1 into B equals to 0. Therefore, B is 0, which is not true. Why? Because as our condition is B is not equal to 0. Another theorem for this is characterization of a subring. The statement of this is a non-empty subset S of a ring R is a subring of R if and only if the first condition A minus B belongs to S and the second condition AB belongs to S for all AB belongs to S. In other words, necessary and sufficient condition for a subring. That is an important property. First is if part, that is called necessary part. Consideration is one of the subset S with respect to addition and multiplication be a subring of R plus dot. Since S is a subgroup of R with respect to addition, for all A comma B belongs to S, that is already given in the statement, then A minus B is also belongs to S by closure axioms with respect to addition. That is A minus B, in other words A plus of minus B, which is A minus B belongs to S, and also since S is closed, since S is closed with respect to multiplication, AB is also belongs to S. For all A and B are the members of S. Then only if, in other words, a sufficient part, let S be a non-empty subset of R with A minus B belongs to S and AB belongs to S for all A comma B belongs to S. Since A belongs to S by condition of 1, that is A minus A belongs to S, which is 0 belongs to S. That is, now A belongs to S and 0 is a one of the identity element under addition, such that 0 minus A belongs to S implies minus A is also belongs to S. That means the closed under for that A and B are belongs to S, clearly A minus B belongs to S. When you add this, A plus of minus B belongs to S. This implies A plus B belongs to S for all AB belongs to S. It means what? S is closed under addition. Since S is a subset of the ring R, associative and commutative axioms under addition holds good in S. Therefore, S plus is an abelian group. Since S is a subset of R, but R is a ring, then associative law under with respect to multiplication as well as distributive axioms of multiplication over addition also holds good. Therefore, S is a ring under addition and multiplication, hence S plus a dot is a subring of R plus a dot. Then one more important theorem is the intersection of two subrings of a ring R is a subring of R. It means what? Intersection of any two subrings is always a subring. That is the simplest statement. When we are observing this by the definition of ring to show this, consideration is take any two subrings, say S1 and S2 are the subrings of a ring R. Therefore, 0 belongs to S1, also 0 belongs to S2. Therefore, 0 is also belongs to S1 intersection S2. It means what? S1 and S2 are non-empties. Intersection of S1 and S2 is non-empty. Again, let us take A and B are any two elements in S1 and S2 such that A, B belongs to one subring, say S1, same elements in the other subring S2. Then their difference A minus B belongs to S1, A minus B is also belongs to S2. Combining them, A minus B belongs to S1 intersection S2. Similarly, the same elements under product, which gives AB belongs to S1 and AB belongs to S2. But both S1 and S2 are the subrings of R. It means that both A minus B belongs to S1 intersection S2 and also AB is also belongs to S1 intersection S2. It means S1 intersection S2 is a subring of the ring R. Then another definition of a ring is normalizer. In other words, center of a ring. The definition is the center or the normalizer of a ring R is defined as the set Z of R equals to a set of A belongs to R such that XA is equal to AX for all X belongs to R. The center of a subring R, the center of a ring R is a subring of R. Now, by the definition of center, take one theorem, that is, the center of a ring R is a subring of R. Just by proof of this is by applying the definition of center, C is equal to set of X belongs to R such that XA equals to AX for all A is a member of a ring. Again, since 0 into A is equal to A into 0 for all A belongs to R, whereas 0 belongs to C and C is not equal to empty. Let us take XY are the members of C. C means center of a ring. Then AX is equal to XA for one thing. AY is equal to YA for all A belongs to R. This is actually based on the definition of a center. AX minus AY equals to A of X minus Y. This is equal to XA minus YA, which is X times, because A is common, X minus Y again by distributive property. Once again, we have to simplify and show certainly center is a subring of the ring R. Thank you.